What is up, you guys? Welcome to another Convex Optimization lecture, where in this one we're going to be talking about unconstrained minimization problems along with their assumptions, some examples such as least squares, unconstrained geometric programming, the logarithmic barrier function minimization, along with interesting algorithms that could solve some unconstrained minimization problems that do not enjoy closed form solutions. We're going to be seeing how descent methods work, and one instance of descent methods, such as the gradient descent methods, that embed line searches within its iterative process. These line searches include exact line searches and backtracking. We're also going to be seeing how the sequence of points generated by descent methods evolve as a function of iteration number on MATLAB. So on MATLAB, we're going to be seeing different implementations of gradient descent using variants of different line searches. So without further ado, let's get started. So as the name indicates, unconstrained minimization problem will involve minimizing a certain cost, let's say f of x, where x falls in the domain of f. As simple as that. So we do not have any constraints that take the form f of I of x less than 0 and hi of x equal to 0. Those are not found herein. Before we proceed in this lecture, we should impose some assumptions on f. The reason of doing so is that throughout this series, we're going to start talking more about algorithms. And by algorithms, we mean that the aim is to generate a sequence of points. Let's say we start by a certain x0, the next point is x1, x2, and so on, right? Till a certain xn. We're going to have to stop somewhere, right? So xn is the last point, which will be the estimate of the minimizer of f of x. So those points should converge in some sense, right? The goal here is nothing other than to minimize f of x. So this sequence should converge as such. F of xk should go p star. And what is p star? It is the optimal value of the problem. So it is f of x star, where x star is the optimal point that solves this problem right here. Now, of course, this sequence that you see, each point, xk, should lie in the domain of f. I mean, that's trivial because let's say you've got an f of x that is log x, as simple as that, a 1D function, log x, as simple as that. Well, none of those points should be outside the domain of f. So what is the domain of f here? It is r plus. So it's all positive, real valued numbers. It's trivial that none of your points, xk, be outside of this domain. So you can't have an xk that is -1, simply because log -1 doesn't exist or is not defined, right? So whenever we talk about the sequence of points generated by any algorithm that is aiming to solve this problem, p, right here, uppercase p, not to be mistaken by lowercase p, that is the optimal value of problem p. All those points, whether we say it explicitly or not, it is always assumed that all these points within the sequence, x0, x1, x2, down till xn, all of those guys should be or should lie within the domain of f. Now this is one thing to keep in mind, and another thing is that my f of x, the cost right here, the cost function, is convex and twice differentiable. In other words, the domain of f is an open set. So why do we go ahead and say that f of x is convex and twice differentiable? Is that all the algorithms that we're going to talk about will actually deal with the gradient of f of x. That is, it will solve the following system of equations. Delta, the gradient of f at x star, is 0. And so this problem, p, right here, is the equivalent of solving a set of n equations and n unknowns. So my x in general is a vector containing x1, x2, down to xn, right? And so the gradient, using the definition, is given as such. Delta f of x is the partial derivative of f with respect to x1 evaluated at x. The same thing with respect to x2 evaluated at x, all the way down to the partial derivative with respect to xn evaluated at x. So by solving the necessary and sufficient condition for optimality of the initial problem right here is the same as solving this guy right here. That is, if we plug x star here, we get del f of x star, that is del f with respect to x1 at x star, all the way down to del f with respect to xn at x star. Each and every one of those guys is 0. So what do we get? We get a system of n equations. So here we've got n equations in n unknowns. Okay? Now you can also, in some references, you can find a more explicit way of writing this as follows. You could see del f with respect to x1 at x1 star, x2 star, down to xn star is 0. Del f by del x2, x1 star, x2 star, down to xn star is 0. All the way down to del f by del xn at x1 star, x2 star, down to xn star. Okay? So this writing is the same as this. Del f by del x at x star is 0. So these guys are my x star, my vector x star, okay? And the gradient is all this guy over here, all the derivatives, all the partial derivatives taken with respect to each and every variable. Okay, so again, I'm going to repeat this one more time. Since we assume that f of x is convex, okay, and twice differentiable, those two will enable going from here, from minimizing f of x, this unconstrained minimization problem will enable us to go from here till here. So in other words, solving p is the equivalent of setting the gradient of f to 0. This is not something new. Actually, you've seen this throughout high school when you're given a certain function to minimize. So fx is, let's say, x squared plus 5x. You work the derivative, that is 2x plus 5. You set this guy to 0, and you go ahead and work out this equation. So you find that x star is minus 5 over 2, right? What we have here is the same thing, but in a general form. So your f is multidimensional because x is a vector, and for multidimensional functions you have to go ahead and impose convexity and twice differentiability so that your x star is optimal. So the aim of the coming lectures around convex optimization is to really work with this guy over here. Now, in some cases, as we will see, a nice closed form solution could be derived from setting the gradient to 0. Let's give an example right now. Let's say your f of x looks like this: ax minus b. Okay, the norm. You take the norm on that, the Frobenius norm or the L2 norm. In this case, you've got your a is in R, let's say m by n, and your b obviously is in R m. Okay, x is in Rn. I'm not going to write, well, I could write this, but we already stated that. Okay. Over here, this function, f of x, is convex. We saw that. It's the least square cost function. Thus, it is convex. We saw that in previous lectures. I'm not going to waste time and prove it again. 1, this is 1. And 2, this is clearly twice differentiable. You could go ahead and work out the Hessian. You could see that it is defined everywhere. So we've got the two conditions that give us necessary and sufficient condition for optimality. And hence, minimizing f of x is the equivalent of setting the gradient to 0. Right? Good. Well, what is the gradient? Okay, so f of x could be written as ax minus b transpose times ax minus b. And so it could also be expanded as follows: x transpose. So if we include the transpose here, we get an x transpose a transpose minus b transpose, all multiplied by ax minus b. And now if we expand this guy, we get x transpose a transpose ax, it's the first term with this, minus x transpose a transpose b, then this guy with this guy, minus b transpose ax, then the last two terms, which gives us a plus b transpose b. Right? Notice that since we're working with real numbers, this guy is the same as this guy. Why? Well, both are scalars and one is the transpose of the other. So transposing a scalar is transparent. So if we take the first term, this guy, let me show you. That is x transpose a transpose b, and we transpose this guy, then it becomes b transpose into a trans. So we flip this guy with this guy, and then we apply the transpose. That is b transpose. Now we flip this with this and apply the transpose. So we get an ax. That is this guy over here. Okay? So those two terms are equal, right? And so why not express it in terms as such? So again, x transpose a transpose ax minus 2, this guy over here. So a transpose, no, sorry. So b transpose ax plus b transpose b. Okay? So this is my f of x. This is the cost function where we started from. And I did all this just to get an expression for the gradient. So now the gradient is easily obtained by setting the gradient of each and every term as such. Now take each and every term. And this gradient is with respect to x, of course, but I'm not going to write that because I think it's obvious. Minus 2 gradient b transpose ax plus the gradient of b transpose b. Now right here, we know that this guy is 0 because it's independent of x. And let's do the linear term and then the quadratic term. So in the linear term, we use the fact that the gradient of ax, or let's say px, right? P is a matrix, is p transpose. So why did I write this fact? It's because that's what we have. Our p is b transpose a. So setting p equal b transpose a, we get that the gradient of b transpose a, which is p, times x, is b transpose a all transpose. So all I did is apply this guy over here, this equation. And which is applying the transpose, it is a transpose b. So this guy over here is nothing other than a transpose b. Now, going to the quadratic term, we're going to apply the gradient of x transpose px is, given that p is symmetric, of course, this, what I'm going to write is applied for symmetric p. This guy is 2px. Now, in the case where P is non-symmetric, I think the formula would be this. So if you're getting the gradient of X transpose, let's say Bx, where B is a non-symmetric matrix, not non-symmetric. It could be symmetric, but let's generalize, and let's say B is not necessarily symmetric. That's the word. In the general case, you'd get Bx plus B transpose X. Okay? Now, taking the particular case where B is symmetric, then B transpose is B, and hence you get 2bx, which aligns with this. So in our case, we've got that P is A transpose A, right? And A transpose A is symmetric. Why? Because if you go ahead and write down A transpose A, you take its transpose, you align again with the same matrix, A transpose A. And so this guy is symmetric, and hence we're going to apply the symmetric formula right here. So this leaves us with 2px, where P is A transpose A, x. And hence you get 2A transpose AX minus 2A transpose B. Now, to get the optimal point, you set the gradient to 0. So del f at x star is 0. Replacing what we got here, over here, we get 2A transpose A x star minus 2A transpose B is 0. Now, you can easily solve this. You get this guy over here. You get a 2A transpose AX star is 2A transpose B. You can cancel your 2's as such. You get A transpose AX star is A transpose B. And given that A transpose A is invertible, then your solution would be, actually you can stop here and you could say that this is what I'm looking for. This is the normal equations of least squares. Now, if you know that A transpose A is invertible, then you got a explicit closed form solution. So if you're given the additional information that A transpose A is invertible, then good. Then your X star could be written as A transpose A inverse times A transpose B. And this is what people usually refer to as the least square solution. Now, this is an example where you get a closed form solution of what you initially tried to minimize, that is the least square cost right here. And here it is, you've got the solution. So you don't need any, well, what I say is not 100% accurate, and I'll state why. But in general, you don't need here any algorithm to solve your problem. You have your solution. It is right here. So given A, given B, you can compute X star. But in many cases, you don't have this solution. You cannot get an explicit solution. I'll give an example just now. In that case, you'll have to resort to iterative algorithms, and the coming lectures as well as this one will be focused on algorithms. And also, in least squares, sometimes it is expensive to use the explicit formula. The reason being is that A transpose A could be expensive. Why do I say that? Well, imagine your n. What are the dimensions of A transpose A? If we go back up here, or let's say 1 million variables, what do you do? Let's say you're on a humble machine. You're on a machine that doesn't have much processing power, or you want your solution as fast as possible. What do? Computing this inverse right here is going to be really expensive. And that's why people would also find interest, even in least squares, where you've got an explicit solution, people could find interest in iterative algorithms. So people would usually work with the normal equations right here instead of a closed form solution. So keep in mind that iterative algorithms are very important whether you have an explicit solution or not. Now, let me give you an example where you do not have an explicit solution. Let's say you're dealing with the following problem. So let's say my f of x that I want to minimize is the log of the sum of exponentials, the sum of an affine transformation of exponentials, that is exponential ai transpose x plus bi, and that's it. So we've got this function. Actually, we've seen this before. We've seen it in geometric programming, and thus this is the cost function of a geometric program. And that's why over here, this guy or this problem to minimize f of x is usually referred to as an unconstrained geometric program. Okay? So this function is convex, we've seen why, and it is twice differentiable, obviously, in its domain. So the domain here is all R, right? Because the sum of exponentials is always positive, and so the log is always well defined. So what is the gradient over here? Well, you could do this by getting one partial derivative and then taking a look at the general form. So in other words, if you want to compute the gradient of f, that is defined as the partial derivative with respect to x1 at x all the way down to the partial derivative of x with respect to xn at x. If you take a look at one of those guys, let's say the kth entry, so let's say I am interested in the partial derivative with respect to xk of the function, so log sum of exponentials of affine transformations as such. Well, this is easily done as, let me make me some space right here. This is xk, not x. So we know that if we're deriving something like this, of log the function of x1 down till xn, then this guy is actually, if we do this, if we make some space, it is actually this. So it is f in the denominator with the partial derivative with respect to xk in the numerator, right? That's what we're going to apply right here. So we get, so my f, right, well, let me call it, I don't want to confuse notation, so let's say I'm going to erase f and call it g instead, just because f is reserved to the log sum of exponentials, so I don't want to define two f's. My g right here is the sum of exponentials, right? So this is my g, and so applying this guy right here, we get my g in the denominator first of all, so it's the sum of exponentials as such, right? And now we want to derive g in the numerator, so the partial derivative with respect to xk of g, that is the sum of exponentials of affine transformations, of course. And we've got I running from 1 till m, right? Okay, good. Now all we need to do is, now since we've got a sum right here, we could flip the sum with the partial derivative, and hence it becomes as such. So the denominator is unchanged and the numerator becomes sum of partial derivatives as such. Okay? So what's left is just to find the expression of this guy. This is really easy. Your exponential of ai transpose x plus bi actually looks like this. If you expand it, it is exponential ai 1. So AI1 is the first element of vector AI times x1 all the way down to AIN xn plus bi. And you're interested in the kth term, so the derivative of the exponential would, so if this is your, let's call this entire sum right here within the exponential as t of x. So the partial derivative with respect to xk of exponential of t of x contains two terms. Okay, so replacing this term right here, okay, we shall get the following fraction where the denominator is always the sum of exponentials and the numerator is the sum, first aik, so multiplied by exponential of t of x, that is ai transpose x plus bi. Okay, good. So this is only one entry of the gradient you see over here, so it is actually the kth entry. So delta f of x, let's say its kth entry, is what we got down there. So the sum of exponentials, and up there the sum of exponentials weighted by aik. And so if I want to be more compact, if I want to write this guy in a vector notation, because as you can see, everything you see is scalar. This is a scalar, 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 right? And the gradient is expressed in vector notation. So if I want to be consistent with vector notations, would be the sum of my exponentials ai transpose x plus bi multiplied by vector ai. Because going back up here, if I stack all those guys one on top of the other in this vector, the quantity that depends on k is the aik, and hence stacking k from 1 till n will give me the vector ai, so which explains why I have my ai here and the rest remains unchanged. Okay, again, since f is convex and twice differentiable, then the optimal solution is obtained by setting this guy to 0, but unlike least squares over here, we don't have a closed form solution. So as much as you try, you can't try to express x in terms of ai transpose or ai bi in terms of ai and bi. This is the best you can do. It is x that solves this equation. And this is why we have to instead use numerical methods or iterative methods to define the solution of this equation. One thing we didn't talk about up to this point is the fact that the algorithms that we are going to discuss for solving unconstrained optimization problems in this series will assume that your initial choice of x0 is going to fall in the domain of f, of course, we said that. But 2, and most importantly, is that the sublevel set S, which we talked about in previous chapters, but we're going to state the definition again, is all x's such that f of x is less than or equal to f of x0. So everything below the value of the initial point, this set should be closed to ensure convergence of the iterative methods. We need to have those two assumptions. Now, for the first one, as we said, is pretty trivial because you need to start in the domain of f. I mean, you won't start outside the domain of f because f wouldn't be defined. And 2, the sublevel set should be closed. You can think about this as, okay, we don't want all my x0, x1 down till xn. I don't want them to be wiggling around in a chaotic manner. No. To ensure proper convergence and to be as tight as possible, we need to ensure that the sublevel set is closed. Now, usually it is hard to verify this, except when all my sublevel sets are closed. That is if you know that the epigraph of f, that is defined by the set xt, where I think we talked about this in previous chapters, right here, if you remember. The epigraph of f is defined by all those couples such that x, of course, falls in the domain of f, but f of x is less than t. So it's all this region that you see in purple. This guy should be closed. So I'm just rewriting the definition of the epigraph. So if you can ensure that the epigraph is closed, that is, all the sublevel sets are closed, you can be sure that your S, which is one instance of sublevel sets, it's one sublevel set, is indeed closed. Now, some edge cases appear where you can, that's it, you can say, oh, I am 100% sure I am working with closed sublevel sets no matter where the starting point is. It's when the domain of f is all Rn, then you could say my epigraph of f is closed, and hence S is closed. This is 1. And 2 is when your f of x diverges, so it goes to infinity, as x goes to the boundary of the domain of f. So one example is your log function. So your log behaves as this. The boundary is over here. And as you can see, your f is going to infinity as x is approaching the boundary of the domain, which is in this case 0, as x approaches 0 from the right. You can have more sophisticated examples. I'm just giving here simple examples, but indeed you could have sophisticated examples such as the log barrier function. So we'll be seeing a lot of log barriers when we in particular talk about interior point methods. More about that in coming lectures, but keep in mind that differentiable functions that enjoy closed sublevel sets, one example is the logarithmic barrier function, and it is of the form sum of logs of affine transformations, so bi minus ai transpose x, and then you take the negative of that. This guy is differentiable in its domain, right? Actually its gradient goes like this. So you've got bi minus ai transpose x, right? And then you've got the derivative of that in the numerator, which is ai. Now the minus cancels with this minus, right? So you've got this guy over here. This guy is defined as long as bi is strictly greater than ai transpose x, which is what defines the domain of f, right? So your domain is here. As long as x is here, this is well defined. So this is differentiable, and this function enjoys closed sublevel sets. So you're free to start anywhere in your domain if you're using algorithms that we're about to discuss, okay? So 1, ensure that you start in the domain of f. This is very trivial. I mean, you wouldn't start elsewhere. I mean, if you're solving this, you wouldn't start where a point where the logarithm is negative. This is naive. And 2, you have to ensure that the sublevel set is closed. Now, ensuring this is hard, but unless you're working in the domain of f is R, n, then you can ensure any sublevel set is closed. And 2, if your f of x approaches infinity as x approaches the borders of the domain of f, which is the case of the logarithmic barrier function, as we approach the border of this guy, which is achieved with equality, you see that the denominator explodes, and hence, but we don't care about the denominator, we care about this function right here. What happens to f of x? This is my f of x, right? F of x will go to infinity, and so this is achieved, and hence we can say that any sublevel set is closed. Okay? Another example is what we were working with right now, which is over here, I think. This log sum of exponential. This guy also enjoys closed sublevel sets. Well, You could see this by taking all this guy down to 0, which happens when x goes to minus infinity. So you're approaching the borders of the domain of the log, and thus the border of the domain of f of x. And so this guy goes to minus infinity, and hence closed sublevel sets. Actually, the solution of the minimization problem of the log barrier function has a very nice interpretation. Let me show you a small example. Let's zoom in over here. Let's say my m right here is 5. So I've got 5 such terms of log bi minus aix. So in other words, I'm minimizing f of x, that is minus log b1 minus a1 transpose x minus log b2 minus 2 transpose x, b3 a3 log b4 a4 and log b5 minus a5 transpose x. Okay? What's inside the log defines a straight line in 2D or hyperplane in higher dimensions. So in other words, let's say b1 minus a1x define this straight line over here. So such that this is my a1, this is a2, a3, a4, and a5. So the problem here is to find x that minimizes f of x. That's what we're looking for by the end of the day. So let's start with some edge cases. Let's say you picked your x somewhere close to the straight line defined by a1. What happens? Well, note that when you're on the line, when you're at the extreme case, you're on the line, then right here you've got b1 is a1 transpose x. So what happens to the log? It goes to minus infinity, and hence minus of that goes to plus infinity. And so all this guy blows up to infinity, right? And so you did the worst case possible. Likewise, if you chose it close to a2, the closer you get to the straight line, then this term will also blow up to infinity. And likewise, if you chose it close to a3, then this guy goes to infinity. Close to a4, this guy goes to infinity. And close to a5, the line defined by a5, then this guy goes to infinity. Okay? So first observation is that as long as you want to achieve the objective, that is minimizing f of x, x star should not be too close to the straight lines. And so an intuitive result would be, oh, why not place x star as far as possible? That is, let's say at somewhere really, really far, let's say approaching infinity. So, well, okay, that of course not explode each and every term to infinity, but in that case, you will lie outside the domain of f of x. Do not forget that this area right here is the domain of f. All this area right here. So this is the dom of f. Okay, so observation 2 is that x star should be within the orange region. So 1 should be not too close to each and every line, and 2 within the orange region. And that's why the best place to put it is at the center. And this is what is referred to as the analytic center of the linear inequalities that are bi strictly greater than ai transpose x. Okay, so that's why you might see in some references, including Vandenberg's and Boyd's book on convex optimization, that the solution of the log barrier minimization problem is referred to as the analytic center of linear inequalities. You can also generalize this. So right here, instead of, if you look at your bi minus ai transpose x, those are linear inequality. I mean, they are affine transformations, and they actually reflect your linear inequality bi strictly greater than ai transpose x. But nothing could prevent generalizing this further to matrix inequalities. So instead of defining my f of x to be log of linear terms, you can have a log det of f of x inverse, where your f of x, uppercase f of x, is sum fi xi, where fi's are matrices. Actually, this is going from 1 till n, and you've got an f0 term multiplied by 1. So in that case over here, your dom of f is the region where lowercase f of x is defined, is when fx is positive definite, because in that case, 1, you can invert, and 2, your eigenvalues are positive, and so you ensure that the log det becomes a sum of, it could be written as lambda 1 of x times lambda 2 of x all the way down to lambda n of x, where lambda 1 down to lambda n are your eigenvalues of uppercase f of x. And not just that, because f of x is positive definite, then each and every lambda is positive, and so your log will be well defined. So the reason I'm writing this down is because, oh, and by the way, this is referred to as, this is the generalization part over here. Your linear matrix inequality, that is uppercase f of x, having it to be positive definite, will actually define an analytic center equivalent to what we saw in the linear inequality part. So your solution of the optimization problem over here, x star, is called the analytic center, same as before, because we're dealing with inequalities, but this time for your matrix inequality. Also, there's a nice illustration for that, but I'm not going to be presenting it over here. So now we're going to talk a bit about algorithms that could solve each and every one of those unconstrained minimization problems. We're going to be dealing with gradient descent methods, and we're going to see different variants of the gradient descent methods, because we know that descent methods generally deal with line searches. We're going to be seeing two different ways of performing line searches, that is through exact line search or backtracking. So let's talk a bit about gradient descent. I actually have some lectures on stochastic gradient descent, but here we're going to focus more on the line search part of gradient descent, because we can achieve gradient descent using different line search approaches. So remember when we said up here that the goal of algorithms that aim at minimizing f of x should generate a sequence of points x0 down to xn? Well, this is what gradient descent does. It's one algorithm that tells you how to generate this sequence of points. And this sequence are going to minimize f of x step by step. Gradient descent is one type of descent method, and that, as we said, they minimize your function step by step according to the following update or recursive equation. So xk plus 1 is your previous x, that is xk, plus a tk and a step on x, xk. This is the descent part. This This is actually referred to as descent update. And why are they called so? It's because for one very important reason, and it's actually self-explanatory. It's because descent, you're descending f of x that you're minimizing, so you're pulling it down. And hence each step should be doing a good job. It shouldn't be, you shouldn't at any step pull up the cost function. And that's why all descent methods satisfy fx at k plus 1. So the new step should be pulled down with respect to the old point. So this is what all descent methods satisfy. Now, unless you hit the optimal point, then situation where all your xk's are equal, and hence by construction all your fxk's will be equal. Okay, so let's say you hit your point, your optimal point that is at 0, and let's say xk reached 0 and stuck there. That means all your f's after this x0 is going to be equal. Otherwise, each f at xk plus 1 should be less than the one that just came before it. So over here, if I take a look at this inequality and I replace xk plus 1 by what I have, that is xk plus tk delta xk. Oh, by the way, we didn't define t and delta. So t, right now we're in a general descent algorithm. I'm not going to say what, well, delta is actually referred to as the descent direction, and t is a step size. T is a step size that you choose according to some line search. We're going to talk about line searches just a bit from now. But what I'm more concerned with right now is the descent direction. We're going to see why it's referred to as such. It's because that's one reason why I didn't define it yet. I wanted to just replace it in what I have right now, fxk as such, and then make you realize each term what it means. So we have this, and remember in the beginning of the lecture when we said, oh, we have some assumptions to impose. And one really important assumption is convexity. And that's where convexity is going to come and play. Well, twice differentiability is because we needed the gradient, and further on we're going to see that the Hessian plays an important role in analyzing the algorithms, how fast they converge, the speed of convergence, these kind of stuff. But convexity is what we're going to use right now in the descent update. Why? Because we saw previously that this inequality, if f is convex, actually means that the gradient of f at xk transpose multiplied by delta xk is negative. So right here you can actually realize that delta x plays the role of what's called the descent direction. It tells you how to descend. In which direction should it descend? Okay? And also tells you the strength of descending. If it's high, descend a lot. If it's low, descend a bit. It's a vector. Its magnitude tells you the magnitude of descent, and its direction is going to tell you the direction of descending, right? Because it's a vector. It directs you how to descend. So in a general descent method, we're not really focusing right now on gradient, the term gradient. I'll tell you when gradient comes into play. But right now, keep in mind that descent methods in general, whether gradient or not, follow the following blueprint. So you first pick an x0 that lies in the domain of f. Then you iterate while you're not converged. So whether you have a certain stopping criterion or a certain number of iterations. One, you determine a descent, delta x, that satisfies this guy right here. That is, so at xk, let's say we're at step k, the gradient f transpose xk multiplied by the step should be negative. This is 1. 2, you apply a line search to choose. Well, you do find in some algorithms that t, the step size, is fixed, right? Well, in general descent methods, the choice of your step size t should be picked by some sort of line search or other variance, if that makes sense. Because in some scenarios you'd want to descend a lot, or you'd want to take a larger step than other iterations, if that makes sense. So over here you've got a line search to choose or to find tk. And last but not least, you've got this update to update your x to generate the next point. So xk plus 1 is xk plus tk delta xk. Okay? And this is the general blueprint of descent methods. Now, where does the word gradient and descent come into play? Remember that here we said, oh, okay, so each descent direction should satisfy this inequality right here. You could actually pick one choice of your descent direction is the negative of the gradient. That is, if you pick delta xk to be minus the gradient of f xk, then guess what? This guy is always satisfied. Why? Because you've got delta f transpose xk multiplied by the negative of the same quantity, but of course without the transpose, which is minus the norm of f of xk, all square. This guy is positive, and so all this thing is negative. So this is one choice of the descent direction. That is the negative of the gradient at xk. And so replacing this choice right here will give you gradient descent. So gradient descent is descent, but your descent direction is the negative of the gradient. Okay? So if you want to see this in a gradient type way, you'd pick this guy. Actually, you'd modify 1. You know what? Let me write it down here. Gradient descent would then, as before, pick x0 and the DOM of f and iterate in the same way while not converged. 1. Pick your descent direction to be the negative of the gradient at xk. 2. Do a line search on tk. More about line searches just now. And 3. Update your x. So now let's talk a bit about the line search part. As I said previously, you could find some variance of gradient descent where tk is fixed. That is, it's t, given to be fixed. That's no problem, but it might suffer from slow convergence. Note that line search would adaptively tune tk to take a large step whenever possible at each iteration. So this line search part, we're going to see in this lecture 2 types. You've got exact line search, so you exhaustively search along array that you pull at point xk. And 2, we're going to see backtracking. So in an exact line search, what you do is at each iteration to pick tk, you'd want to find the best t, given to be positive of course, that minimizes x plus t delta x. Of course this is xk, tk, and delta xk. Now in some cases you can find an analytic expression for tk. We'll see this now in a MATLAB example where we're going to animate how x is going to move, whether you use backtracking or exact line search in a gradient descent type method. You're going to see that indeed tk could be obtained using a closed form solution. So now if there's a closed form solution, good, we can embed that. And if not, you have to exhaustively search for t. This is not tk, this is t, it's a variable over here. So don't forget that this is a 1D function. So calling this guy g of t. So really, you're just minimizing g of t. So numerically, what you do is just exhaustively generate different values of g and pick the t that corresponds to the smallest g, as we'll see in the MATLAB example. That's in case you don't have an analytic solution. And later on in this course, we're going to be seeing efficient ways of performing exact line searches. But keep in mind that line searches are usually inexact. Why? It's because the step size is chosen to more or less approximate f along the ray x plus t delta x. So in this case here, g, if I could plot it, let's say your g looks like this. So this is your g, that is f of x plus t delta x. And note that this is a negative gradient and gradient descent. So given that t is positive, you're just reducing f. So in other words, if t is really small, there is a t, think about it that way, that there is a t pulling it downwards that will, by the end of the day, minimize f. So this is an inexact way of reducing f. Another way could be achieved by gradually reducing t until we find a straight line that lies totally below g. Note that in the exact line search way, your tk would be chosen to be here. This is the t that minimizes g. It's right here, right? So t, this is t. Let's say k, that is right here. But according to exact line search, there is a problem in exact line search. It's because this will highly depend on the discretization step. So if you generate a lot of points, okay, you might hit this point. But what if not? What if you don't have much time? Because remember, you need to do this at every iteration of the gradient method. And that's where backtracking seems to be efficient. Backtracking will actually choose it to be over here. Let's call this tk back. So how does backtracking work? It doesn't need a discretization grid. You don't need to generate g at each iteration. You don't need to generate different points of g to find the minimum. Instead, what backtracking does is it starts at g, okay? So you start right here. Well, what I mean by start right here is that you first choose your, let's say your t to be 1 in an attempt of finding tk back. So t1, let's say it will lie somewhere, I don't know, maybe here. This is t1. You evaluate your g. So g at t equal 1 is nothing other than f of x plus delta x. If this guy is larger than f of x plus a multiple of alpha, which we give to the algorithm usually between 0 and 0.5, times t times the gradient multiplied by the descent direction. If this is larger, then reduce t downwards by a factor of beta. Oh, we didn't write it. It's actually f of x plus t delta of fx transpose times the descent direction. This is what it is. So as long as your black curve is on top of the green line, this is your black curve. As long as the black curve is on top of the green line, fx plus t delta of fx transpose times the descent direction, reduce t. So if you're here, reduce t downwards by a factor of beta. So while this is true, instead of t, plug in t times beta, where beta is fixed to be between 0 and 1. So t will take the following possible values. 1, you initialize it to be 1, then it will be beta, then beta square, beta cube. And note that this sequence is decreasing because beta is between 0 and 1 until you hit, till the green line lies on top or is equal to g. Okay? So really, those are the methods that we're going to be implementing in MATLAB, seeing how we can converge to the optimal value numerically using the following sequence of points. So let's go to MATLAB right now. Let's go to MATLAB and open a new file, call it, I don't know, gradient with exact line search. Actually, gradient descent with exact line search. So let's do a CLC and clear all. And let's say I want to, let's go back to the board, and let's say okay. You're interested in minimizing the following function. So f(x) is half x1 square plus alpha, or not alpha, plus theta x2 square, where theta is or should be positive, or else f is no longer convex. So let's apply gradient descent, first time using exact line search and the second time using backtracking, and see how things go on. So the gradient right here, we need the analytic expression. So here we've got two entries. The first one is the derivative with respect to x1, and the second one is with respect to x2. So if we derive f with respect to x1, all we get is half times 2x1. And if we do the same thing with respect to x2, we get a 2 theta x2. That is nothing other than x1 and theta x2. So this is all we need to run our gradient descent, whether with exact line search or with backtracking. And let's see how things go on. So again, if I open MATLAB, I need to define my f, that is a function of x1 and x2, right? As we said, it is half, so half times x1 square, we go x1 square, plus theta times x2 square, so theta times x2 square. And theta, let's say for no reason, it is 10. So this is my f. And we also want the gradient, let's call it df. It is a vector of two variables, so it's a 2D, so it's a 2 by 1 vector of two variables. First, we define the two variables, x1, x2. And second, it's a vector. First entry contains x1, and the second entry contains theta times x2. Okay? So I'm not going to talk, so over here I'm going to run my gradient descent method, and right after I'm going to do some plotting of each of the generated sequence points, x0 down to xk or xn, whatever you want to call it. And right here, I will not include a stopping criterion. The stopping criterion is nothing sophisticated. It's just that I'm going to limit my number of iterations. Let's say I'm going to execute 100 iterations, as simple as that. Okay? Note that, of course, due to the structure of the problem, due to convexity, more diligent choices of the stopping criterion exists. You can have a stopping criterion based on how far fxk is from a certain point, or how far, fx k plus 1 is far from fxk. If those 2 points are too close, then stop. How close, you enter a certain tolerance value, let's say epsilon, I don't know, maybe 1e minus 3 or 10 to the power minus 4, something like that. For the meantime, just for demonstration's sake, I'm not going to include a stopping criterion based on the magnitude of at 2 consecutive iteration points. No, I'm going to just limit the number of iterations, okay? And we're going to save all my x's in one matrix, call it x. So at each iteration, I'm going to stack my estimate x. If we go back here and we take a look at gradient descent, we could see that the first step is to choose x0 in the domain of f. Well, right here my domain is all Rn, so I can choose any x I want. There's no limitation on that. And guess what? Also, since I'm working in all Rn, then according to this guy right here, we have that our sublevel set at x0 is closed. Since my domain is all Rn, that's pretty cool. I don't need to care about S, whether it's closed or, I mean, I don't need to verify. I know it's closed because I'm working in the domain of all, because the domain of F is all Rn. So I don't need to worry. So my X, I'm free to choose it whatever I want. I'll choose it to be, let's say, theta 1. And that's it. So if I want to go and apply my gradient descent, I start my x0 in the domain of F. So this is my x0. It is in the domain. It is in dom of F. And so now I'm in the loop, right? So here goes step 1. That is, choose dx to be the negative of your gradient. So this guy right here is the gradient. Choose it to be the negative of your gradient at x1 and at xk, right? So my current xk is x. So I evaluate it at x. Okay, so this is step 1. That was choose the descent direction, which in gradient descent is the negative gradient. Now step 2 would be to perform line search. In this script, I'm going to implement exact line search. So if we go back to the lecture right here, the exact line search is going to involve an exhaustive minimization of t, right? So right here, we need to generate all my g's. Imagine, I need to generate all those. This is pretty exhaustive. It's not an easy thing. Well, on MATLAB, it's really easy. You can do this with one line of code, but numerically, you're doing a lot of computations. That's not good. So we need a t-axis. So all my t values that I want to generate my line, that I need to generate my g. Note that the minimization is strictly positive. So no t equals 0. So I'll start with a small value, let's say epsilon. And I'll take steps of 0.01 and I'll take it up to 10. Okay. Next, I'll generate my g. How do I generate my g? Well, it's f of xk plus t delta k, right? So we go f first x1 plus t times dx1, right? And then x2, I'm doing this entry wise. That's why you see 1s and 2s. Plus t times dx2. So this is my g at the moment, right? Actually, if we run this, let's see how g looks like. I'm going to put a breakpoint right here just to show you how it looks like. And we've got an error. Unrecognized function or variable t. And that's because I didn't define t. Why? Oh, this here is at every t in the t-axis. So t-axis. And same goes for this guy. So run. We've got it right here. And plot g versus t-axis. So this is how g looks like. If we zoom in right here, what is the minimizer? It's not 0. It's not 0. I mean, it's not let's take some steps right here. It's not epsilon, which is 2 times 10 to the power minus 16, as one might think. It's not 0.01. It's not always the first point. I mean, if you look at it from here, it might look like, oh, it's at 0. It's somewhere, or it's the first point in t-axis. Well, it's not. Zooming in, you see it's somewhere around 36.82. It's at 0.18. Well, to get this point, you can use MATLAB's min function, or find min. So you go find g equal to min g. This will return the index in t-axis, and so you'd want to map it onto t-axis to get your t. So if I open the console right here and go run again, it's 0.18. Okay, this is only in the first iteration. Note that this is repeated at each iteration. So that's an exhaustive job, huh? Let me close all. And I'm not going to be plotting at each iteration. Well, if you want, I will, just for presentation's sake. But if I want to launch the algorithm, there is no need to plot at each iteration. Okay? So this is the second step. The last step is the descent update step. That is nothing other than your new x is your old x plus t times dx. Simple as that. It is right over, where did we write this? It's right here. Exactly. It's this guy right here. So this is what we did in step 3. Okay? Actually, it was written down somewhere here. Yeah. This is step 3, the update method. Okay, good. So now we should have all the points. Okay? Now, just for, presentation's sake, I'm just going to show you how G looks like at each iteration. So run. This is G at the first iteration, second iteration. Let's see the values of T if they're indeed changing. So, yeah. Clear all, CLC. Run again. 0.18, 19, 17, 20, 16, 22. So this is an adaptive step size, right? You can also save the T's to see how they look like. T save. This is not a step. This is just we're saving the values of T. So T save. We'll just append T at each iteration. So now I don't need the plotting. All I'm interested with is T. So run, plot, T save. So here's your T. This is how it looks like at each iteration. 0.18, 19, 17, then 2, then 16, then as you can see it's wiggling. It's wiggling in a certain pattern. There is a pattern that you can draw from this iterative procedure. This is in case you want to save your T values. Now let's do the plotting. What I mean by the plotting is I want to plot x0, x1 down to x an iteration. So you can do this as such. You plot x1 versus x2, let's say in O's. So this is how it starts somewhere here. This is your starting point. Then you iterate like this. This is how the algorithm is working. A plotting that seems to be more fun would be, let's say, my x values. Let's say you want to animate how your point moves at each iteration. That would be a bit fun. And that would help you maybe understand how gradient descent is working. So you'd open a figure. Hold on, because at each time I want to plot a point. First time you'd plot the first point, say in red. and we'll fill it with red as well. And we're going to limit the axes between min and max of my x1 values, so my x, and min and max of my y values. Let's put some grids and turn on box. Now, so if I run this, I'll only see 1 point because that's what I plotted right here. And I limited my axis to min x, to min and max x, and min and max y. Now let's plot the others using some sort of animation. So for k equal 2 to length to n iteration, so that's the size of x, this point, 100. So at each time I'm going to plot a new point in the same way, draw now, and pause for half a second. So run. Here you see the point moving at each iteration, approaching 0, the minimum, the optimal point of the unconstrained minimization problem. Let's have a bigger, the points were small, let's increase their size, so marker size. Let's set it to something like 10. Same thing here, and run. There you go. Point starts at 10, 1 and decreases down to 0 at each step of the gradient descent algorithm. Okay, good. So this is gradient descent algorithm implemented using exact line search. To be more expressive, you can include an x label as x1. I'm going to use an interpreter of LaTeX. And the same thing for the y label. I use x2. Running this, there you see x1 and x2. And here's the animated figure. Okay, now this is exact line search. Well, let's do the same thing, but this time we'll call it gradient descent, but using backtracking. And I only need to change one part of the code, that is right here. So this guy right here, I don't need it, because we're going to be implementing backtracking instead. And in backtracking, as we said, backtracking was the last thing we explained. We're going to be iterating according to this loop. Okay? So we need to define an alpha, which is between 0 and 0.5, let's set it to 0.25, and a beta, which is between 0 and 1. And this controls the factor step size. So if beta is too large, then it would take a lot of time to approach to the appropriate t. And if it's too small, it might jump over it. So let's set it something between 0 and 1. Let's set it to 0.5. And right here, you will initialize each time t to be 1, and then perform this while statement. So as long as your fx plus t delta x, so x1 plus t times dx1, same thing for the second entry, so x2 and t dx2, as long as this guy is greater than or equal to fx, or x1, x2, plus alpha times t times df at x transpose times dx. As long as this is true, then shrink down your t by a factor of beta. Running this, there you go. It's a different pattern, huh? This is a different pattern. As you can see over here, it's faster. It took off faster than exact line search. And there you go. It's approaching 0. There you see it. Okay. You can also take a look at your t values, which obviously takes on a different pattern, but there's a repetitive pattern, as is the case in exact line search. And yeah, but nevertheless, in this particular example, we could have done all this thing without backtracking and without exact line search. And the reason being is that the problem in hand has a closed form solution for the line search. Let me show you why. So remember that we're trying to minimize fx plus t dx, right? So going down here, if you want to find at each iteration your tk, that is the arg min of fx plus t dx, then what you're doing really is replacing this in here. What you get is x1 plus t dx1 square plus theta x2 plus t dx2 all square. Minimizing this is equivalent to setting the gradient to 0. So calling this guy g of t, because it's a function in one variable t, and that's what we're minimizing. Then g prime of t is 2 dx1. Well, you've got a 2.5, they cancel. I'm not going to write the 2. So dx1 times x1 plus t dx1 plus, same thing, dx2 theta into x2 plus t dx2. Setting this thing to 0, what you'd get is x1 times dx1. I'm interchanging delta and d. Usually I say d for delta, so in case you hear me say d, I mean delta. So x1 times dx1 plus t dx1 square plus theta x2 times dx2 plus theta t dx2 square. All this equal to 0. So the terms depending on t is this and this, so we'll keep them on the left hand side and we'll factor with respect to t. So t into dx1 square plus theta times dx2 square is equal to minus x1 dx1 plus theta x2 dx2. So your t is minus, it's a closed form solution, there it is, it's a function of xk and dxk. K stands for kth iteration, so at each iteration you need to do this, you need to compute t according to this closed form expression, plus theta x2 dx2 over dx1 square plus theta dx2 square. Okay, let's implement this instead of backtracking and exact line search. See what we get. So if we go back to MATLAB, I copy paste all this code except for the second step right here, because we have an explicit closed form equation for t, call it gradient descent underscore explicit. So over here, all I need to do is compute this guy right here. So I have a fraction that involves x1 times dx1 plus theta times x2 times dx2 over dx1 square plus theta times dx2 square. Simple as that. So running this, let's see what happens. Run an error telling me x2 is not defined. Well, of course x2 is not defined. Of course x2 is not defined. This is x of 2. Run. And there you go. It's being minimized. Okay. There you go. Look how elegant it is. And one interesting thing that I think is, let's see how my t looks like. So plot t save. Whoa. And there you go. It's a fixed t. At each iteration, it's a fixed t. It tends to be fixed around 0.18, right? So this is actually telling us that the best t is fixed. It's not adaptive, if that makes sense. Despite the fact that x is being adaptive and dx is also changing at each iteration, well, t is not. T is telling me, oh, do not change. The best t for each iteration is 0.1818. And look at the accuracy. It's up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal digits. Let's try changing theta and see what happens. Let's disable this plotting right here. I'm not interested in looking at x. I'm only interested in the t values. Let's say my theta is 2. I disable all the plotting, and I'm only going to plot t save. So run. There you go, 0.66666666 and so on. That's the best t. It's fixed. Notice that in the previous, if I disable plotting and backtracking, for example, and if I plot t save, it is wiggling around certain points. And same thing in exact line search. So if I plot t save, there you go. It wiggles around 0.18. It's wiggling around it. Okay? Okay, good. And actually, if you notice, since t has an explicit closed form equation, since dx also has an explicit closed form equation, which is x1 in the first entry and theta x2, and so you can write x at each iteration through an explicit equation as a function of theta and n, the iteration number. I'm not going to do this over here. You could just replace t and dx and see what you get. You can arrange stuff seen as a function of theta and n. I'm going to stop this lecture over here. I think we covered a lot of stuff concerning unconstrained minimization optimization. We started off the lecture by defining what an unconstrained minimization problem is. We stated conditions concerning algorithms that will iterate until converging towards a minimizer of P, problem P, the unconstrained minimization problem. These iterative methods, such as gradient descent or descent methods in general, or as we will see in future lectures, steepest gradient descent, Newton's method, self-concordant methods, and so on. All those methods will rely on one thing. The core essential of each of those algorithms is working with the following system of equations, setting the gradient to 0. We gave an example where you could derive explicit closed form solutions from f of x, such as the least squares. It does have an explicit closed form solution. But others, unfortunately, do not have closed form solutions, such as the unconstrained geometric program. It doesn't have a closed form solution, so we should resort to iterative methods. We saw the logarithmic barrier function, its minimization, will also not enjoy a closed form solution, and so we also have to resort to iterative methods. We gave a nice geometric interpretation of the solution of logarithmic barrier functions, because its minimization will be crucial when talking about interior point methods in future lectures. We introduced you to some algorithms that fall under the category of iterative methods for unconstrained minimization problems, such as descent methods in general, and one instance of descent methods, that is the gradient descent. We also saw that gradient descent methods include line searches, such as exact and backtracking. And last but not least, on MATLAB, we implemented 3 different variants of gradient descent. One that relies on exact line search, the second relies on backtracking, and the third one relies on an explicit equation for the step size t at each iteration. We also saw how x moves at each iteration. So for a certain cost function where its minimum point is at 0, we saw how the points converge towards 0, whether I'm using backtracking, exact line search, or the explicit t solution. So yeah, if you enjoyed this lecture, please leave a like on the video, subscribe to the channel. Also, if you have any questions, you can leave a comment down in the comment section below, or you can send me an email, whatever you prefer. But please, I've been receiving a lot of emails recently about homework. One thing I'm going to say, and I'm going to insist on, is that I do not do any homework on behalf of anyone. It is unethical. And so please do not send me any homework questions, or don't send me any problem and tell me, please Ahmad, try to solve it. No, I'm not going to respond to such emails. If you have a question regarding convex optimization, or regarding anything I said through this lecture, or maybe an ambiguity that, you've been reading a book, or you've been trying to solve a problem in a book and you're stuck at a point and you need some guidance or something like that, I'll be happy to reply to the email, and maybe we can have a Zoom conversation or a Skype conversation, whatever you prefer. And this happened previously with other students. I had students contact me. I don't charge those students because I believe that they were inspired somewhere by my lectures. I really admire that. And if they have questions concerning my lectures, I'd be more than happy to assist. So if you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions, don't be shy to ask. And if possible, you can consider donating to my Patreon account any amount you wish. But if you cannot, it would be super helpful if you could subscribe to the channel. That would help the channel be more exposed. YouTube would show it to much more people of interest, and so I could reach a larger audience. Thanks for watching, and I hope I'll see you in future lectures.